so the theoretical aspect is about the Einstein gravity, whether it is really satisfactory from the theory point of view. As everybody knows, so that's the effective field theory. All the field theory should be understood as effective field theory. For example, then every theory has some upper limit beyond which the theory will not apply. So there's always the valid range. So if you start from the string theory, for example, and come down to low energy, then it's going to be the expansion in terms of the curvatures. And the first term is going to be the linear term. That is nothing but the Einstein gravity. However, in principle, there can be quadratic, cubic, and the higher orders, definitely. So that means from the field theory point of view, our theory cannot stop here. As long as we believe in string theory, Einstein gravity theory should be approximation and not a full theory. Another thing is that in the Einstein gravity theory, we have a very fine tuning. So extremely small number or large numbers depending on how you define. So the most natural time scale in gravity theory is Planck time, which is extremely short time. But our universe age is very long. So in any way, you may always say the natural unit, natural scale, and the scale that is provided by Einstein gravity. Then you will see that there's a huge gap. Finally, for many reasons from the theoretical point of view, sometimes we'd like to study gravity theory beyond Einstein. One example is the so-called n-type physical space with a negative cosmological constant. I was informed from Professor Lee that here one of the research topics is about holography, where this kind of ABS space gravity is quite important. So that's not the Einstein gravity. So from the theoretical point of view, there are many reasons why we should go beyond Einstein. Now, how about the observational aspect? That is about the so-called standard model of the cosmology, ΛCDM. This is based on Einstein gravity again, and with some assumptions to explain our present universe. So turns out that it works pretty well. Many observations that seems to be consistent with this standard picture. However, there are some challenging observations nowadays that may really make that make us to think about ΛCDM whether it is correct or not. So some quite serious and challenging issues. There are many. One of them is so-called Hubble tangent. I'll explain about a little bit more, and also cosmic birefringence, so sigma 8 or SA problems, and etc. I just focus on these two.
Excuse me, so sigma 8 make it disappear, right?
Yeah, so nowadays they say that now there is no more sigma 8 problem. So I will not mention at all, but at least that seems to be the general opinion now.
I see.
Yes, very recently. But still, I guess some people seem to be arguing why S8 rather than S12 or something, so some arguments. Okay. So first, Hubble tangent. The thing is that this is the how fast our universe is expanding. Problem is that it seems to depend on how we measure. One measurement is based on the cosmological microwave background, CMB, which is coming to us right after decoupling time. So in terms of redshift, when redshift is about 1,000, so if you hear the present redshift is 0, for us, so 1 plus z is always so you can convert that easily in terms of temperature or whatever. So now it's a 2.7 Kelvin. So z equals 1,000 means multiply 1,000. So about 3,000 when the universe was 3,000 Kelvin. That was the time that the universe became neutral. So all the light will come to us since that time without any interference. So if we use that information, then our expanding speed is 67 kilometer per sec per megaparsec. That's the Hubble tangent. However, we can directly measure by looking at our close to us, look at the galaxy, and they will be receding from us, measure that speed, and then directly you can see what the speed is, expanding speed. That's actually bigger than this number. These are the error bars. So up to about 5. So that's what Hubble tangent is. So it's a 5 sigma discrepancy. So in terms of statistics, this may be still 5 sigma, even though it's not, it's not really conclusive yet. Usually people accept it's a really completely disagreeing if it is more than 6 or 7 sigma, right? But it's a really significant at least. Another thing is cosmic birefringence. This is the birefringence means depending on the polarization, the speed of light is different. So you may see that effect. That's essentially cosmic birefringence. So we mentioned that cosmic CMB will be coming to us from z equal to about 1,000 to now without any interference with any other things, so no scattering whatsoever. So there is some circular polarized right-hand side way and the left-hand side way. The vacuum or with a metal, that is somehow make the refractive index different. So the plane of polarization will be rotating. So it's a rotation of the linear polarization planes. And that angle has been measured very recently. But the statistics is not that really good. So we may say that there is some rotation. And if you want to say, no, it's just significantly within the error bar, then you may say that beta equals 0 is excluded at the 3 sigma level. That's another way to express. And then all these kind of things. Now, I mentioned only these two. The question is how to resolve it. So to resolve it, we have to go beyond Einstein gravity. That is a necessity. Going beyond Einstein, Einstein gravity was lambda CMB means we are introducing some additional degree of freedom. It can be some fields like a scalars, or it may be really changing the metric by introducing higher curvatures. So here today, what I'm going to do is to introduce some scalar field and think about some models, so-called early dark energy. Okay. So early dark energy model, what is the early means? So this is a scheme for our universe, starting from the Big Bang. It was radiation dominating, and then the energy between the radiation and the matter were equal. And then until at this time, it's all plasma state, so all the atoms are ionized. However, at some time, as the temperature cools down, the electron and the probe will be combined to form hydrogen atom. Then, since that time, our universe will become neutral. So that's the combination time. And however, rather recently, we know that here. This is matter. Equation of state of the matter is characterized by a single parameter divided by density. So radiation domination means this we are changing we are introducing some fields at early time, and they will play some role so that at the present universe observation, it will make the Hubble expansion parameter a little bit larger. Hubble from the CMB was 68, around 68. And doing something here will make it about a little bit more than 70. So not much different from the direct measurement based on the supernova or the variable stars, say. So that's the what I mean by early. And just by passing, nowadays one of the big issue is about the observation by Deci, according to which dark energy is not constant anymore, but changing as a function of time. But however, I thought I drew something here, but that disappeared somehow. So anyway, so there will be some modification here. That's what I'd like to do. And all the Deci results are related to the late dark energy, all the observation. And then here, rather than so z equal to -1, so it's going to be so all average, I guess it should be something like here. I think I did made the wrong things, only the 70%. But anyway, the value will be sometimes lower than -1, and can be 0.7. It's a time-dependent variation. So what kind of model will predict that? That's the whole story of the late dark energy in a sense. But I am not talking about that. I'm concentrating this part. Okay. Okay. Now, what is the early dark energy model? So we are introducing some scalar fields, which is extremely light, like axion. And there are some other models which actually we work on, but here we will work on this ultralight axion-like model. So specifically, the model that we'd like to study is introduce some scalar field, and then we are introducing some gauge field also in general, and the potential of that. So here, this scalar field may be from the particle physics, it may be from some symmetry breaking of this global U1, so-called Petrarch symmetry, and etc. for the actions. Anyway, so what it gives us some real scalar field. Here, if you see phi near 0, so phi equal to 0 is the minimum of this potential, right? And if you take a look at the close to phi equal 0, so this parenthesis, inside parenthesis is phi square. So it's an nth power of phi to the 2n. So this is roughly speaking some power of behavior near the origin phi to the 2n. So I'll measure later, but if n equal to 1, that's a phi square, which means massive theory. But if it is n equal to 2, 3, 4, like bigger than 1, then it's a higher power. So it's a massless. I'm saying that massive theory and the massless theory is very different. So here, what we'd like to do is n equal to 3. It's a massless case. I'll come to that more.
Excuse me. So
Okay.
go back. So in your model, so the U1 gate field is a hidden factor, right? Or is a traditional
No,
electromagnetic?
this is really our usual electromagnet.
Utilized.
This is our CMB.
I see. Okay. Okay, thank you.
Okay. Okay, now, so first let me explain you how this early dark energy model make the tangent less about the Hubble tangent. Here we'll drop gauge field term because it is not essential in explaining the Hubble tangent. So by adding that, we just did also by adding that. But by the way, this is not what I did. All these, much of the part will be reviewed. And I'll just come to the point what we did later. So here, the potential is we can write essentially what we do need is a 2 parameter and also this the power. So n equal 3 is what we'd like to take. So here we drew some the potential graph. As you see here, if n equal 1, it's a quadratic. So near 0 is a 5 square. So it's a massive theory. But if n is bigger than 2, 3, 4, it's a flat. 5 to the 4, 5 to the 6, and etc. is a flat. So naively, since I'm very slow and I like a simple thing. So the potential is like flat potential, then wall. Okay, then we do know everything. We learned the quantum mechanics. That's the way I will visualize. The real calculation is complicated, but the quantitative aspects can be understood by this kind of picture. Okay. So then we have Einstein equation. In other words, all the methods will determine the expansion rate of the universe. And also we do need some scalar field equation, time derivative, or in terms of dimensionless derivative, natural time given by the Hubble parameter inverse. And then to solve these equations, we do need initial condition for this scalar field. We'll take the initial condition so that it will start from near the top. So we'll consider n equal 3, mostly because it works best. So n equal 3 and near the top. If it were at the top, it will just stay there classically. But if it were very close to the top, it will stay classically very long time, then eventually slowly roll down, then quickly come to the bottom, oscillate. Okay, that's the solution, and I will not even show you the detail of the solution. Okay, I think I may have some solution here. Okay, so here, as you see there, the solution is that in terms of Z, bigger Z means all universe. In the all universe time, it's staying very close to the top. Then it's a constant potential for value. Then it is nothing but the cosmological constant. Okay, so the scalar field energy is we have a kinetic part and the potential, but if kinetic is negligible, pressure is a minus V, and energy density is a V, so W equal to -1. So the if potential is dominant, that's essentially dark energy with a W close to -1. So that's what is shown here. So essentially, stay there just like a cosmological constant, then rolls down and then oscillates here, and then goes to 0. Okay, that is the solution you can understand easily. Now here is the graph. So here we will adjust the parameters so that near Z equal to 1000, the rolling starts before about some 1000. they will stay at the top of the potential. So it's like the cosmological constant is a constant, then rolls down here. If you plot their radiation, then radiation is 1 over scale factor to the 4th power.
哦，它就退出。
Okay. So and the dark matter is 1 over h to the cube. So this is the later time direction. Later time, this violet color matter will dominate, but earlier time green color radiation will dominate. So it keeps dominating. And later, this after equilibrium, the metal will be dominating. Okay. However, during this period, it's like a cosmological constant. You may worry that is the universe exponentially expanding? No, because dominant energy is actually radiation. Green color is keep going up. And this energy is just about 10% or something. So in other words, if we just plot here the fraction of the energy carried by dark energy among the whole energy density, in other words, raw dark energy divided by raw total, is always not more than 10%, and it is localized only during this time. Okay, so this is the thing that will eventually make us the present CMB observation value bigger, like a little bit more than 70. So we are changing that part with this scalar field. Okay. Okay, and also here we have some parameterization. So very far away, A goes to so much later time. At a later time, this W parameter will be Wn. So it depends on n. But if n equal to 3 or bigger, then Wn is bigger than 1/3, which means they are decaying faster than radiation. So this n equal 1 is 0, 0 is the relative matter, 1/3 is the radiation. So which decays at 1 over h before, but bigger than minus or bigger than 1/3 means they are decaying faster. So much faster than radiation. So later time, their contribution is negligibly small. So in other words, in the early dark energy model, the scalar field will affect physics only in this region, and they will not affect later universe. So we don't have to worry about any other effect. Okay. Okay. So that's the essence. And so maybe better not to go to the details here. So let me just skip all these perturbations and essentially here by this perturbation we'll see some sound speed and the sound speed change which will be related to the Hubble parameter values. But I don't want to go to the detail of that except saying the final results. So here, and so the first here we mentioned the parameters that we introduced. We introduced some the early dark energy model compared to the ΛCDM. Since we introduced new scalar field, we do need some extra parameters. That extra parameters can be written in terms of the shape of the potential, etc., or other observables like what is the fraction of the early dark energy density at some peak value. So I showed you that the fraction of the early dark energy was about 10% or so, around z equal to 1,000. Okay? So that at what time? So that should be about some 1,000, 3,000 or something. That's the ZC. And at that peak time, the fraction of the all dark energy, those are the information that we do need. So actually in the graph, we saw that it's about 10%. Okay. Okay, then, so here, so the more detail about parameters. Here, let me just briefly say that the main thing is that we have, in addition to the ΛCDM model is based on the 6 parameters. So in addition to the lambda parameters, early dark energy needs 4 parameters in terms of the Lagrangian parameters here. Or you may say that those of Lagrangian parameters in terms of the more observables, which is related to this, like the peak, the time of the redshift at which the early dark energy will be maximum, and also at the time the energy density of the dark energy, and etc. So that's the another way of parameterization. So here is altogether 10 parameters, and this has been done by these gentlemen, and then they showed that compared to the ΛCDM, where the Hubble parameter was 68, as you remember. However, in this, with this extra 4 parameter added early dark energy model, if you choose n equal 3, for example, you get 70. So compared to the direct measurement based on the supernova, which was about 73, the difference was much smaller, right? So it's rather than completely solving the Hubble tangent, it made the tangent much less significant. That's what we can say.
Sorry, what's the constraint value for the mu, the mass parameter? I remember that's approximately 10 to the minus 5, right?
I think so. So I do not remember in terms of.
I think just go back to a few slides. I think
Right.
there's the one.
Okay. Okay, here I think we have. Okay. Here. You mean the in terms of
Yeah, mu.
parameter?
Yeah, I remember there's a slide say that's 10 to the minus 5.
I think somewhere I may have said that. Let me see. But that's not any more the mass directly. So if n equal 1, it is related to mass, but we are not.
But this mass is not the mass of the axion, right?
No.
It's not
It's
mass.
not.
Okay.
And the axion is only for n equal to 1 case.
Oh.
And so we are talking about n equal to 3, where the mass is it's a massless. I think I understand your question. I wrote somewhere, but maybe somewhere here. Let's try to
yes.
find later.
Yes.
Okay. Okay, so that's the essentially story, and since we keep working with some parameters, here is some summary about the ΛCDM parameters. We do need a method of the information, so baryon and also dark matter, also dark energy, and also some other parameters, spectral index, etc. And those parameters are be written in terms of these notations, NSS, this scalar spectral index, and etc. So it's a red colored one and the values. Once you know all the red color values, all other quantities, including Hubble parameter, can be calculated based on the ΛCDM model. That's the message. We do need 6 parameter input. Now, if you have early dark energy parameter, early dark energy model, then you have also additional 4 parameter here. I dropped n equal to, since we chose n equal to 3, but the n is also a parameter, so there's a 4. So it's that's the whole game with this model. So to repeat the same thing here, so the early dark energy resolution of the Hubble pendulum is there. As a result of this early dark energy model, it will change the affect the sound horizon, and eventually it will eventually make the Hubble parameter somewhat larger value. For example, here, let me see here. Hubble parameter here. Black color. I mean, this gray color is the from the shows the supernova observation. So here is about 73 or something, and ΛCDM is orange color here, 60 something, and these are the n equal 2, n equal infinite, n equal 3. So if you see this violet color, then it will be sitting in between these two. So the previously it's really close to the 6 sigma difference, but here the difference is quite much reduced. Difference between the supernova based one and based on the ΛCDM with the introduction of early dark energy is quite much reduced. Okay. Now let me move on to the other topic, which is cosmic birefringence. Okay. So as we mentioned, the cosmic birefringence means the propagation speed is dependent on the polarization, right-handed or left-handed circular polarization or linear polarization, or whatever. And for this to happen, parity violation is very critical because it's really parity transformation related. So without, so in the theory, without parity violation, you don't have any this phenomena. However, do we have any parity violating theory? Of course, in the particle physics, weak interaction, but this is not weak interaction phenomena. So we have to introduce some parity violating term. So the idea is that here we'd like to introduce parity violating interaction through a Chern-Simons term. So here, this one. So this one is this F field is our gamma photon field. Photon scalar. So essentially, the early dark energy is interacting with our usual CMB photon. However, this term is breaking parity. As a result, the propagation will depend on the polarization. And then the thing is that whether we can just, among others, calculate this coupling constant in a proper value so that it agrees with the observation. That's the whole game. Okay. So here again we have this potential, but we are concentrating on n equal 3 case, and this coupling constant we call early dark energy coupling constant. And this F was a scale for scalar field phi action constant. And the rotating angle depends on how long it travels. So it's a sum over the whole time since the less scattering surface, when they left one, less scattering surface, then there's no interaction especially. And until present time, they keep changing. So essentially what is important is the difference of this scalar field value. Okay. And we got the phi value, right? Starting from some top value to the bottom value. We are using that one. So that's it. So by testing some page for the polarization, all the information about the polarization, you may say that in the linear polarization x and the y direction, there is a phase. If the phase is the same, it's linearly polarized. If it is not, in other words, if the difference is not zero, there must be some delta I wrote. Delta, which is the difference between these phases. If delta is not zero, then it's an elliptical polarization. So, however, if you just approach from the this is a very fastly changing one. So we'd like to time average over, right? And then what is characterizing the field is this maximum value amplitude of the x linear polarization and the y directional linear polarization value and the phase difference. However, these are not observables because we are not measuring electric field directly. We are measuring only intensity, which is square of those. Okay, so these are the square of those, and we can just define these things. So, for example, so sometimes the notation is in terms of S notation or IQUV notation. So this the total intensity, and this one is S1 is when so E0 y equal to 0, then this value is 1. So in other words, if Q equal to 1, that means if you have some horizontally if you have some polarizer which will admit horizontally polarized one, that will be corresponding to this one, because at that time Q equal to 1. That means without any vertical polarization admitted. And also U is the one which is 45-degree linear polarization. So these are more physical quantities, but I will not go more detailed. But the important thing is that these are the actually so-called Stokes parameters are what we usually measure, and through that we can really see the effect of the birefringence. Okay, so how do we do that? Actually, the Q and the U parameters can be decomposed in terms of the E field and the E modes and the B modes. And it's just Fourier transform of those. And we are interested in the cross correlation. By the way, here, the E modes and the B modes, relatively, the parity is opposite. So as a result, cross relation, so here is that even though we are talking about the E modes and the B modes, then we have also EE modes, BB modes diagonally, and the EB modes of diagonally. Right? But as we mentioned, B modes are parity odd. So red colored ones are parity odd. So we do need this quantity to see the birefringence. And there can be also the CMB temperature things. Here you can also write it. So anyway, so the essential the result is that parity violating quantity is EB mode. Essentially, we have to see this EB modes cross spectrum terms. This is the thing. There can be also TB modes. And that was when we measured usually the temperatures in the older days. That's the most parity sensitive one. But nowadays, we can really measure actually so EB modes. So that's what we will talk about here. So when we just had the CMB, the CEE was the dominant one here, and But however, see, BB modes can be generated by nonlinear effect, actually. And actually, that nonlinear effect has been observed. But these are still all parity preserving. We want the parity violating term. And this red color parity violating term can never be reproduced without any parity violation in the theory. Okay? So we do need parity symmetry breaking. Now that's the main the basics about the theory, and all others. I mean, since we are given the Lagrange and the setups and things, then we can really do the numerical analysis. Here, people actually, SK et al. Did this one in 2023. This is the first paper that reported this one. So they just run here all the parameters except the coupling constant. In other words, they run here so out of the 4 plus 6 equal to 10. They run 9 parameters for fixed couplings and found the optimized value. This is the thing. This is the optimized one. One is without Hughes data, and another is with Hughes data. Hughes data is the observation based on the supernova. So if you have a supernova, that's some distance ladder. But to do that, you do need really some distance. So for that information, if there's a galaxy in which there's a supernova, you want to find some the variable star in the same galaxy. Then with that one, you can see the actually the distance. That's the way they are calibrating the distance and measure the expansion rate. So this is the what with the source data. So as a result, the final result is that these black ones are the data. As you see, it's a really very big error bars, right? So this is CEB, parity violating correlation. That's with a very big error bars. And with this, either you use green color or blue color. That's the best fitting you can do with this kind of parameter value to minimize the chi-square values. So so that's the what happens. And if you do the so-called forefront values, then you may see that it may fit better here. You may see, or quantitatively, with this one, you have actually smallest chi-square. But in general, based on only this way, you fit, and you cannot fit better than this number. Okay. So that's the situation. So if you read this author's paper, PRL paper, then you will see that their conclusion is that by that first run the all the 9 find the optimal values, and then they try to find the coupling constant. That's the way they did, and then concluded that ED model with n equal 3. They are not well supported by the CMB observation. So that's the thing. So in other words, here important thing is that so fixing all the 9 so except the coupling constant, they run the all the 9 parameters, find the optimal values. Then they start the coupling constant. By that, they conclude that it does not fit well with the data. They are not agreeing with the data. That's the conclusion. Okay. Now, so far, that's not my work. And our work is actually the different way of fitting. In other words, on the roughly speaking, rather than explaining detail, here there are all 10 parameters. Here is 9 parameters. So all ΛCDM parameters and 3 EB parameters. And then here there's additional the EB coupling parameters here. What they did was actually first find by running these 9 parameters here. Here, let me see. Running these 9 parameters for given GD and find the best fitting. Or for different value of the GD by running 9 parameters, they find the best region like that. So in a sense, these are the kind of way they search the parameters. Our point of view is very simple. Why don't we run all the parameters together, get the best value? So it's a very, very different philosophy, because it's like the corresponding to whether to search only in this region or the search the whole region. And the Eskils et al. KRL paper conclusion is that by doing this narrow region, so for given GED, they just first fix 9 parameters. They by that way they cannot reproduce the observation. But we are running the whole the range at the same time. Okay, it's a very simple difference, and the result is very different. That's what I'd like to mention now. Here, as we mentioned, in the Eskils et al., for example, they just fix the 9 parameter. Then they run the EBE, the early dark energy coupling parameter, the Chern-Simons couplings, and then found the value like this one, fitting. By this one, they can get chi-square value of this one. And the some other approach was Pauling et al. Was the other side. And they are the 9 parameter values they chose, depending on the green color one or the blue color one. Our result, so is very different. So for example, so this green color one is the Eskils et al. 2023 PRL paper, and they are saying that they are not reproducing quite well. So this orange color is what we did, running 10 parameters all together. Then as you see, so just by an eye, seems to be fitting very much better. Do you agree? It's much better. Or more quantitatively, by chi-square, we have a much smaller value compared to the 76. We have a 68, so better. So in a sense, so it fits better. So that's why we are saying that we can also explain the consistent way this birefringence by this way of parameter search. Okay, so this is a kind of reproduction. So here, what we tried to do was the green color is let's say the blue color is the best fitting values that we showed. Then we intentionally, for one parameter, one by one, each parameter, we increase the value 10%. That's the green color. And decrease the 10 by 10%. That's the orange color. So best fitting value, around the best fitting value, we just increase the parameter a little bit, decrease parameter a little bit. So here we have all the parameters set. In this case, for example, EBE or omega baryon, here you see the compared to the blue color, green dot and the yellow dot, not much different. Right here, green dot, which is a 10% bigger parameter, red dot, which is 10% less parameter value, not much different. However, for some parameter like this of C, so this is the best fitting one. If you increase 10%, very different. Reduce 10%, very different. They are very sensitively depending on the parameter. That's why running all parameters together is very important. If not, you may not find the right spot. Okay? And also theta is the same thing. So here the conclusion is that there are many parameters that are insensitive. However, there are some parameters which is very sensitive to the values. So the sensitive values I wrote here as a red color one. Of course, those red color ones of course are dependent on the essentially not the ΛCDM genuinely, but the early dark energy parameters. So some of those early dark energy parameters should be dealt with together with the ΛCDM all together. Okay, that's the only way that you get right values. And we did a similar plot for the GEBE and the H0. So that's a little bit bigger than the so 70s, and those are the fitting the all the parameters. And also this is another plot, for example, the Hubble parameters and the GEBE we can reproduce. For example, here if you see this one, Hubble parameter, there's the average a little bit more than 70s, as we showed here. Also, this is a similar without any Chern-Simons term, but with Chern-Simons term, we will also get similar results, and also GED parameters. So here, that's the what we got.
Oh, sorry, you have fixed the n equal to 3, right?
Yes, that's right.
If n equals to 3, then the early dark energy decay diluted as a radiation.
That is right.
But according to my experiment, if it's a decay like radiation, the H0 can no larger than 17.
F0.
H0 can
H0.
yeah, it's approximately like 17.
17.
70, yes.
So maybe are you based on the ΛCDM?
No, the early dark energy model, that PRR paper.
Okay.
Only when you decay faster than radiation, then it can slightly larger than 70.
Yeah, that's what we got. So here, let me see. In the early part, we showed you let me see here.
Yeah. That's that table you just showed, yes.
Right.
Sorry, that's 70, yes.
Yes.
Yeah.
Because N=3 is faster, decaying faster than radiation. Right. So it's not one of the radiated. It's a really negligibly small contribution at the present time, and numerically, as you said, you are right. This is the thing.
Yeah. So I'm wondering how can you get such large H0, like 72? Yeah. What's the difference between this model and your model?
Okay.
Yeah.
First, here we have also Chern-Simons term. So that's one thing, and so as a result, the parameter values are also a little bit changed. ΛCDM parameter. So let me see.
So you add an extra parameter from the Chern-Simons term.
Right.
And does this Chern-Simons term contribute to the potential of the early dark energy? Maybe it rises a little bit of the early dark energy, potential energy. So
I mean if phi is even though it's a quite small number, right? It's almost zero. If it is constant, how should I say? Time dependent. Okay, let me see. Your question is how can this be that big, right?
Yeah. Oh, I see. Your fraction of an early dark energy is like 19%. That's a very large number. Yeah, usually it is
Right,
5%.
Or 10%.
Yeah,
Yes.
5 to 10%.
10%.
But this is a very large number. So that's why you get a very large.
Right, that's right. But this is by running all the parameters together. And then, so maybe to rephrase your question, with this somewhat large numbers, will it not be affecting any other observables that we used to know in the ΛCDM? My naive answer is that early dark energy is really localized near the Z equal few thousand, and the effect to the later universe is not good. So I think, usually at least we do need about 10% or so, but it should not really confined to be 10% or what you're saying is 5%. It can be a little bit larger or small, and it will affect only the physics.
Yeah, I understand. If it's decay faster, you can have a larger fraction of early dark energy.
Right.
And I suspect that the transemittance cause an extra effect for the decay rate. So it might cause a faster decay rate for the early dark energy. But I don't know how. Yeah, and let me think about how the transemitter can cause a faster decay rate.
Yeah. So we did this for the Hubble parameter also with including the Chern-Simons term, but usually the Eskils et al.'s work for the Paulin et al., I guess, so for the Hubble parameters was without any Chern-Simons term, because even without Chern-Simons term, just all the dark energy part, without any character violation, that it can explain the Hubble tangent, right? The reduced tangent. So here we have not really compared those two things and to really single out the role of the
I see.
the Chern-Simons term related to the Hubble parameter. But I think that's a good question, and I haven't thought about this comparison myself much. But yeah, I agree that it's bigger than usual because of this one. I think that's a good observation.
Okay. Yeah.
Okay, so essentially that's it. What I wanted to say. So the main message is that we just revisited early dark energy model with n equals 3, and then by searching the whole parameter range at the same time, not only the Hubble tangent problem, but we can also get the better consistent results for the birefringence result. That's the main message. Okay, thank you very much.
Thanks for a nice point. And I want to, I'm still trying to understand the early dark energy model you're talking about. So can you remind me what is do you have any special reason for, special motivation to study the n equals 3 model rather than the others?
Okay, so let's see, what would we do? Okay, here, n equal 1 is of course the massive theory usual action model, right? And so it does not work, and so I think essential point is this one. To me, we want early dark energy affect physics near the T equal or T decoupling time in the early universe, right? And that effect is to increase the our present day Hubble parameter, right? But not affecting later universe, because if we have a scalar field, that's a problematic always, right? If we have something still now, so we want it to be decaying very fast. Okay. So in other words, we want the W of that scalar the bigger, so that it decays faster.
I see. So N equals 3 is like kind of the boundary condition, critical.
Yeah, so 2 is like a radiation. We are adding one more radiation. So at the present time, we have one more component. So then I think it should be serious, because the massless ones are countable now, right? What is the G star now? So massless one is a photon and some extremely light neutrino, some neutrinos, I don't know, right? And having one more massless, I think that's a serious. So in that sense, N equal 2 is dangerous to me. I'm not an expert in cosmology from the gravity or field side. So then this one sounds good. Most economical. So it can be 4 or 5, but 3 is already, if it is faster decay than radiation, well, negligible.
Okay, and also about this figure, the figure, the blue lines, yeah, and obviously there were some oscillations, and I guess it comes from the potential oscillations.
Right.
If I understand correctly, the duration of the oscillation should be determined by the mass or something other parameters about the action. Yeah, actually, I'm asking which parameter or which quantity determines the duration of such kind of oscillations.
Okay, so let's see. Maybe in the action, what is the parameter do we have? Here, I mean, we are neglecting the this transcendental term, right? We are talking about only the potential, right? Parameters in the potential, either V0 and the F should define everything. Or I just rewrote those things in terms of others, but essentially, shape of the potential should define everything.
And in this model, how many parameters do we have to determine?
In the potential?
In the potential.
2. If you are not counting power n, if we count also power n, it's a 3.
Okay, yeah, we just fix n equals 3, so there are 2. Okay.
Yes.
And also, I'm confused. What is the full name of the
Ultralight Axion.
Thank you.
Yes, sorry about that. Okay.
And one more question about your work. It seems like you did some comparison using the same data, but you're analyzing the data in a more, complete way. So it seems like you consider the parity evaluation by introducing the Chern-Simons terms.
Yes.
Is this part neglected by the work you're talking about? A work from PIL, right?
No, so let me see. Let me see. In the Hubble parameter issue, parity doesn't matter at all.
Sure.
So when we talk about the Hubble parameter, whether you put putting this transcendental term makes your theory more complicated unnecessarily, in a sense, right?
Yeah.
But yes. But however, once you are related to the birefringence, parity violation is critical. If not, you can never generate EV cross power spectrum time. So that's so that's the major thing.
Yeah, I just want to know that why can you get a better fitting compared with the
Okay. So maybe I may show this one again. If you so in a sense it's like a parameter search issue. If you first pin down one parameter value, then find another parameter, you are not fully searching the parameter space.
Okay.
It's like the square shape or this band. That's what people have done. But we are doing is really sweeping out the whole plane.
But in that sense,
But eventually our value is not far from their values. But as I said, some parameters are quite sensitive to the graph, right?
right, even if we
Here.
show a little bit about the parameter that they fixed by them, we can get a much better result.
Right. Because some parameters are very sensitive. But by reduced parameter search, assuming that we do know how to fix the ΛCDM parameters. Okay, so we have an EB model, and then so 4 new parameters, but the 3 of them together we vary and find the value, and then finalize the coupling constant. That approach is really narrowing down the parameter search. But we did not impose any such thing. Then even though we are our parameter is of course not very far. So rather than this square, we are not very far away. We are very close to this square region. For example, green color, very square regions. But in the previous method, they are missing that. And assuming that it's really not that sensitive, then it should have worked, right? But some parameters are very sensitive. So that's why they missed and concluded that this model cannot reproduce the observation data.
And what is your conclusion about the model? I mean, the constraint for the model, because you get a better fitting, and maybe the model would be allowed.
Yeah. So what we are saying is, the green color is what the PRL paper, and yellow is what we got. So seems that we have reasonably agreement with the observation, which can be proved by chi-square. Statistically, so better. So we may say that it's a consistent. Unlike the green color, which they say not reproduction.
But for small L, it seems like here.
Yeah. So
But it's fine.
yeah. So I guess in near future, if the error bars are becoming very small, then less controversial. And we have some other issues that we fought with some referees and finally gave up and submitted for this. But that's a little bit some different story stuff. Anyway. Okay, thanks for the question.
Yes, related to the question. So here we see to make a clear conclusion, the quality of the data, in particular the EB spectrum, is very important.
Very much.
Yeah, I mean the quality of the data. You see the present data, the error bar is so huge.
Yeah.
We cannot make clear conclusion. So do you know when the new data will be released in the future? Maybe any plan?
Okay. I'm very bad at such the observation. So on the plans I don't know.
I see. So Japan has a plan to satellite to be.
I think I think I may have heard some future plan for this one, but simply my memory is so small that the information went out. I heard but went out, so I don't know.
I see. Maybe in the near future we cannot have high quality data. Maybe within 5 years, within 10 years.
I think it's always statistical errors if you have more and more data taking. So it's just a matter of time. The statistical error will be becoming smaller and smaller after some limit.
Okay.
Right? Because it's a number of observations. But really, the error bars coming from the limit of the instrument, that's another thing. So I think that's I don't know.
Okay.
Of course, Planck data, that's over. Right?
Yes,
that's
that's why I asked you this question. You have answered this question.
Right. So Planck data is over, and I don't think.
Because the Little Bird Japan project.
Yeah. So what I do not know is whether one of the major goals is to really getting this cross power spectrum or not. That one I am not sure. I just take a look and look up the one and also ask some guys who knows much better than I on these things, and I will check.
Okay. Last question. So here about your model, Chen-Simons model, because there is no first principle to write the Lagrangian. So I think the potential, the coupling are ruled by hand. So my question is, are these results, are sensitive to the potential or to the interaction you choose? Yeah, because we can modify the coupling, right? In particular, for the Chen-Simons term, you can the linear interaction, the GFF tilt is a linear interaction. In particular, we know from some top-down theory, this coupling can be very complicated, like a coach stage. If you consider this kind of new coupling, so I'm curious. So how can this change your result? In a large change.
I think the potential shape will definitely change their results.
Yeah.
However, the reason why this kind of potential is introduced is that we'd like to understand phi scalar field as an angle kind of because it's related eventually the U1 angle. So so U1 global symmetry breaking. So that's why sine or cosine is naturally coming in. Then we'd like to make a minimum at phi equal to 0. Then I think so 1 minus cosine phi is essentially the only combination, right? And then the only remaining thing is the power. Without any power, that's the simplest thing, and that's what is related to the action mark. So this is a natural extension of that. Question is whether this can be obtained from some non-perturbative effect of the quantum field. That's the separate issue. In other words, how to, among the infinitely many possible choice of the potential, why this kind of potential?
Yeah.
But it's in a sense a natural extension of the action, and that's the first thing. And the second thing is that maybe n equals 3. If the U1 symmetry is broken to some discrete symmetry, like a quantum instant, etc., then this kind of power may be occurring. I don't know.
Yeah, no, because as an effective theory, we typically consider all possible couplings. In particular, this axion can couple with x squared, right? Like a Dileton field. Yeah, this can modify the story, maybe modify the story a lot. Yeah.
Yeah, so this phi is action coupling to the photon field. Yeah, so this coupling, isn't this more or less unique?
Not unique. We know like a coach, the function. It's okay, still okay. And
Or
we
you
know
know
from
coach phi?
yeah, coach phi. It's still okay.
Well,
It's not axiom, and we know many constructions from string theory or string gravity.
well, I just say I made an expand the coach phi near phi equal to 0. Then it's
Yes,
power.
and the
and
small phi is okay, but the
Yes.
finite phi is different, and this may change the story. And maybe can make the data more better with observation. That's my comment. And particularly if in the future we have high quality observation data, maybe we can use some new techniques like machine learning to learn the best copy that can fit the observation very, very good. Yeah. But the first we should have the data.
So in that sense, yeah, this is the simplest.
Yes, I see. As a toy model, it's simply to try. Yeah, I see. Yeah, I agree. Totally agree with you. Yeah. Okay, thank you.
这是可以for example, the backfield here has no relation with the inflation on this and that kind of thing. It's just appear in the radiation dominant period.
So yeah, that's what I try to make clear. So if you can relate this scalar field that occurs, that plays some role here, to the really early inflation time, that is really fantastic. But since it's very hard to connect because inflation, inflaton will by after hitting is no role essentially. But suddenly here they have to start from some value top of the potential, right? Initial condition. We need some mechanism. So at least to me, it's not easy to connect the early universe inflaton or late time, this one also. So we say this will decay faster than radiation. So essentially 0. Then suddenly playing some role here late time. We do need some mechanism. We have to introduce something. You know? So naturally, I think it seems very hard. But if there's some natural mechanism, it would be interesting.
Will cycle. The air EB, right? In the pink.
Think
Right.
about that energy. Oh my God. I just copied and sorry about it. Thank you. Thank you.
Okay, I think that's so much for the question parts. And if you have a further question, you can ask him directly. Okay, let's send Professor Lee again. Yeah. And we're supposed to come back at 3:30. Yeah. 10 minutes delays.
Then have a rest. And we can
Okay.
start at 40.
So come back to 3:40. Okay. 对，我要去打印一下，我去打印一下。
你下哪个地方让他们签？
你要完美打印，
这个
我上去，这个让
这个方面对，让这两个对吧？
这两个对，
证件号码是吧？
需要填证件号码，
还需要他
还要
护照的复印件吧？
一个签字，
要
对，
复印件吧？
要复印件，
我们这可以邮件让他们用。
可以邮件。
Oh, 6, so yeah, we can try. So
Yeah, we can try.
maybe we can.
Yeah, I have. 不是，他现在一个人没有半天没有这种动态。OK，
export on new percentage value.
Oh, you have
other
porter
If it's not possible, then probably I can make a PDF file.
Yes.
Yeah, let me It's not easy. So here
So let me get you just
So I may start by
Wow.
它只有一个口。哦，
Manuel Bridge. No, I have not seen. I have not seen in very long.
Yeah. We can
overlap in research. Okay,
Okay, good.
okay. I see. Okay, so you may already.
都不是，这些都不是。啊，这个拔不了，你要拔，你要拔。
And when I come back, I may you are and where is your name?
Oh, it's just the Saturday this weekend.
How can you be here?
Oh, wow, yeah, that's so maybe tomorrow or tomorrow.
Okay. And when shall I visit your place? In May or next time?
To you, so.
When it is in May, you will just have the later time.
Why was it?
I see, yeah, because you are married. So let's think about you come here like something. Oh,
因为他最后现在查的比较严，跟所有人都签
他不查谁来吃饭？
机密案，巡视组呀，有考到吗？他签没事，其他人就是其他老师签一下。对，香港让他们 speaker 签一下。
不查说的是。
你巡视组进度量搞得很被动。
想问一下，就是对这个引力的弱场近视，就是说现在是在做这个超辐射的这个半循环，它现在是这么一个问题。找一下这个图。
让云龙欠一下。
就是它这个是个半径，然后这个是超过设计的这个黑洞，然后现在它要做的是从这个黑洞周围，在有了半径之后这个不规的变化，然后它这里是给了一个就这个表达式。
要不明天吧，明天上午吧，这会儿有个报告，好吧？
哦，
对，
I'll see you Friday. Oh, when did you come? That's Thursday. It's like you're got here Thursday. We met in Oh, yes. Thank you very much. What did I need to
你记得的那次
怎么这么晚？
不是，这属于那是你签过的，这属于他们的这个对话。
我在哪签？这两个地方，
对，
现在
一是然后
一水不足，都确认了，是所有委员行吗？还是都想要一水不足？先来的。
因为上次是签一是不足，
三个都可以。
哦，你也三个，
对，看起来还合适。护照。
上个写的这样啊，上个是平面的。这个属于他们学校的任务。
we know, when is今年今年是 this way.
我觉得
今年 I mean the person who
yeah.
What is it?
Very close to here.
今年
Yeah.
今年
So far the Asian Pacific ICP.
Okay,今年 is ICP.
It's very close to here.
Another one. That's the same way as KIT.
I think so.
KIT.
Yeah, it's a different cloud.
I see. So he's not using these features.
All right. Yeah, this is the KIT.
Yeah. Okay, but later.
Later does not work because this screen is special.
I see.
Okay, so time is up. So let's move to the second talk of this seminar. And in this second talk, we are very happy to invite Professor Kim from the Guangdong Institute of Science and Technology. So he obtained his PhD in 2009 at Stony Brook of New York University, and then he conducted 2 postdoctorate successively at the Southampton University in UK and Amsterdam University in New Zealand. And then he is now a professor at the Guangzhou Institute of Science and Technology at Korea. So he will give us a talk about machine learning approach to holography towards holographic strange methods. So let's welcome. Yes.
Thank you very much for a very detailed introduction. So actually, I was just wanting to visit Professor Lili, but he kindly he gave me an opportunity to talk. So today I'm going to talk about these machine learning things. Maybe one of the reasons I just chose this topic is that I want to get some feedback from the people here. I would like to be very slow, and I'm not going to try to explain the technical aspect of the machine learning. So it's another story. My point is how to use this machine learning technique to study physics. Okay, so before starting, this is my campus, and it's here. The Guangzhou is here, Seoul is here, and maybe Beijing is somewhere here, right? So it's not that far, just a 2 hours flight from here to here. From here to here, it's the close in terms of time. It take more time. Okay, so I guess many people are familiar with just the basic concept of the holography. In essence, it says there's some gravitational physics. This represents a black hole, and you can imagine the screen here. And the quantum field theory or quantum system lives on this boundary. And for example, this quantum system can be quark-gluon plasma or high-density superconductor, and this is black hole. And you can see this white one or green one, this kind of effect of this space-time or black hole. And the effect will determine the property of the quantum physics at the boundary. And so regarding the machine learning, we can ask 2 questions here. Here is a quantum system, and there is a space here. We call this a bulk space-time. And one question is, can we understand this extra dimension? This is the field theory direction. There is extra dimension. Can we understand this extra dimension as a deep neural network? It's a quite interesting question. Or regardless of that question, can we use a deep neural network as a useful tool for holography? It's just a technology. We have 2 questions, and I would say the answer is positive for both. Today, I'm not going to talk about the first question, but I'm going to focus on the second question. Okay, so the schematic understanding of the deep learning is just technique. Traditionally, we study applied holography can be studied in this way. We start with some gravitational model. And this is basically model building as a speed of the bottom of holography and make a prediction. And that prediction should be compared with the experimental data. Is it okay? Oh, I see. Ah. Okay, well, let me continue and make a prediction. And if this theoretical prediction does not match with the experimental data, then you go up and you change your model, okay? And you do again until you get the agreement between the prediction and the experimental data. That's a traditional way of research. And if we use the machine learning, then instead of doing that, we start with experimental data, it's a big data, and machine will tell you about the gravitational model. And by using this model, you can make another prediction and try to make another experimental data to match the experimental data. So then this way of research, I would call this an AI method. Okay, so this traditional method, in order to study this, we need intuition or some principle to make a good model here. So we need sometimes genius to think about a very, very good model. However, this AI method, we don't need a genius. We need a machine, good machine. The machine will give us a model, and we just use that model to understand the physics. And if it works, then we try to understand what happens. Okay, so I think this is an important thing. So sometimes people say machine learning answer does not, say anything about the physics. I think I would agree, but we are human beings. So after knowing the answer, we try to understand the principle. Then if we can understand the principle, I think that's why we use the machine learning. So not just knowing the answer is not enough. But as you know, sometimes there's a very difficult mathematical problem. But once you know the answer, sometimes you right away understand what's happening, right? But the knowing answer may be difficult. So then for that, we may use the machine learning. That's my point. So normally when we study the science, so we are very familiar with these model building things, or sometimes we use the very big supercomputers. And now, in a supercomputer, we also can use the machine learning type understanding. And this machine learning now are used also the string theory. And this is the review paper for the string theory. And here is deep learning, ADS-CFD holography, says something about my talk here. And also this is another review paper. Here there's a theoretical particle physics. It's also using machine learning technique. Okay, that was a general introduction, and for a specific purpose, I'm going to introduce this paper. This paper is by Professor Koji Hashimoto in Kyoto University. I learned the original idea from this paper. And when I read this paper, I realized the basic idea also can be used for general problem, not only holography. So I just made a simple paper. The title is ADS Deep Learning Made Easy, a simple example. What I did here is the machine learning technique here, I just used to solve the classical mechanics. The main purpose is twofold. First, I want to deliver the main idea by using the simple example. Then people who does not know about anything about holography can understand what's going on. The second, more important purpose is I need a train. I need to train myself to solve the problem. So I just chose this problem. Problem is very simple. This is one-dimensional motion. You may imagine there is a gravitational force. And then there may be some mysterious force depending on this position. But we don't know what it is. Then we have to solve Newton's equation to understand the trajectory over the final velocity of this motion. Then this is basically F equals ma. This is ma is F. And this force has a gravitational force and this mysterious force. Okay. Normally, what we are doing is if we know F, then everything is very simple. We can just solve that. But suppose this F is very complicated and we don't know what it is. Then traditional way is we use some intuition. For example, somebody can say, okay, F is if it's a friction force, then maybe it's proportional to speed or proportional to speed squared. But I just chose this is put F is a function of X. It's a little bit mysterious force. But suppose there is some force. then we don't have any principle. You cannot guess anything. Then mathematically, probably you will try some polynomial form. For example, ax plus bx squared plus cx cubed, something like that. And you just compute numerically and try to compare with here, my big data is initial position and initial speed. You have many data sets here. And at the final position, you have a speed. That's your big data. And we have to find out force matching these big data. Okay. Then again, let's go back to the principle. So you will maybe you may want to assume polynomial form ax plus bx squared plus cx cubed. Then now you change a, b, c, and try to match the final all big data. Okay, that's the normal traditional way. Sometimes it works, but if it does not work, then probably you want to add more terms forever. But this is not so clever way, but that's one way. Now, my point is, instead of doing that, just we can hire the machine, and then we can just ask machine to do that instead of by ourselves. Okay, so this is the simple result. This gray one is the true force fx. I just made it. So, and then machine start with this red one. This is random. Machine start with a random force, and then machine just try to repeat by changing the force form, and at the end of the day, after 500 trials, machine just found the correct form. This is green. How machine finds it? Just doing this. We know the experimental data VF. For example, we have 100 of the experimental data, and the machine just guess any force. Then of course the final VF will not match to the experimental value. Then you just think of the difference, right? Experimental one or the trial one, and you just add the all difference. That's called the loss function. Then try to remove loss function to vanish. Okay? You try to vanish loss function by changing this F. And at the end, machine succeeded to reproduce the correct F. Okay? So I don't explain how machine do that, but let's accept we have a very good machine and just ask machine to do that. Does it make sense? Okay. This is basically what causes it for the global thing. So, this is not the code's original way. This is another way, but I just explained the basic. Let me just summarize the basic understanding here. You have a big data. Big data, you have a many experimental data, initial speed and position, and final velocity, final speed, right? And then you use that, and you try to solve numerically this ordinary differential equation. And the machine, this is machine part. This is a new deep neural network. I'm going to explain this later, but the main role of this part is machine assume F, just randomly, right? And just solve this equation. And here, this is experimental result, the large V, and V is the machine's result. Because F was random, of course, this is not zero, should be different. So some number, let's say 1 or 2. But you have a 100 experimental data, it may be 100, something like that. And you want to make this 0. That means your the machine's answer should match to the experimental result. Until then at the end, if this is 0, that means F is correct. Okay, that's the basic idea. Okay. Another interesting problem is this integral problem. So this is a disk. And imagine there is a charge distribution on the disk. There is a radial symmetry. So that's why this charge distribution is only function of R. And you can measure experimentally the electric field strength on this G axis. Okay. Then in the general physics textbook, you can find out this the formula. So this is sigma. If the sigma R is given by integral, by this integration, you will get the electric field on this Z axis. Okay. So you can immediately see once sigma is known, just integral is easy. Now you can imagine the opposite situation. You don't know sigma, but you can measure electric field experimentally on this z-axis. This is given, then the question is what is sigma? That's the question. So this plays a role of the big data because this electric field strength should match with every position, every z position. Then we have a big data here. And the same story, this is the machine's result. The machine, actually, this curve is the assumed charge. This is a real, true value. But the machine will start with some random distribution like this one. And you put this one here, then of course EG does not match with the experimental value. Then the difference is a loss function. And the machine now try another one. Okay, this one, and do that again. Try another one, do that again until this becomes 0. And this becomes 0, that means now machine just trained the correct charge distribution. Okay.
Yeah, I think in this setup, the solution is not unique.
Very good.
Right. There are many different.
Very good. That's a very good point. There's a possibility of the multi-solution, of course. That's a good point.
You can cook many sigma.
Sure. Yeah. There's a possibility of multi-solution. In order to avoid the multi-solution, I would say this should be complicated enough. Then it's okay, but this is too simple. So there's a possibility. Yeah, I agree.
And in this practice, how many layers?
In this case, we just chose 3 layers.
3 layers.
And then maybe 3 or 5 nodes, very simple one.
I see.
Yeah, very good. Okay. Good. So I'm going to come back to that point later. But here, my point is I want to deliver the main idea. Okay. So I just explained 2 examples. How to solve OD and the integration. But you know, the physics is full of differential equation and integration. Then this technique can be applied to many physics problems if you are interested in the inverse problem. Okay, so let me try to generalize. So what's happening is the first example is this F is unknown. So the point is everything is known, then numerically solving differential equation is straightforward. Then suppose you don't know F, then you are using the big data as a boundary value or initial value. Then you have to guess, or machine have to guess what will be the answer. Let's generalize. This is one specific example of this general form. Then this red one can be unknown. Now your problem is you have to solve this equation, but A, B, C, F is unknown. You don't know that. Then how to solve that? Of course, you cannot solve. Then you are given lots of big data as an initial value or boundary value. Then what machine is doing is this. Machine try A, B, C, F randomly and try to match all boundary data. If it does not match, that means loss function. And here loss function is the machine's result minus real true result. So that's the loss function. If loss function vanished, that means you found the correct A, B, C, F. And that's what machine is doing. Let me generalize once more. There is only one function F and only one variable Z. Then here I have a coupled equation. I have 2 functions F and Z, and now I have unknown A, B, C, D, E, F, G, H. But you know, the complicated problem, but the basic principle is the same, right? The machine is trying to find out these red ones by using the boundary data. Now, so the reason I generalize it this way is to explain this equation. So you don't need to understand what this equation means, but the mathematical structure shows there are 2 functions, ax and phi, and they are function of z. So it's in this form, right? And here this f is unknown. It corresponds to the in-breaking factor of the background of matrix in the context of the holography. So now this AX is basically gauge field in the holography, and this phi is some scalar field, and this AX has something to do with the conductivity. And in holography, the conductivity will be computed by the boundary value in the holographic direction. So now you have an experimental value at the boundary, and you have a parameter, then you have a big data at the boundary. And in order to match the boundary data, you have to choose the correct F. Okay? That's the whole structure of this method. Okay? So my point is, if you can solve this problem, of course you can solve the others. Okay? That's the idea. So about this integral problem, let me generalize. So this can be understood like this. And there's some functional. The functional has two functions, F1, F2. In this case, F1 can be sigma, but no F2. But in principle, you have more functions. And this is the integral over R, that's the holographic direction. And you have some parameter, alpha. You need this parameter because you need the big data. So every alpha will give every value. So that plays a role of big data. And we can generalize once more. This F1 and F2 can be the G can be a functional of the other functional. And you have these coupled integral equations. Okay. And this A alpha and B alpha, you have big data, and you want to find out small F1 and F2 in the integral. Okay, so the reason I generalize in this way is to show this equation. Again, so let's just focus on the mathematical structure. Here, this L is function of Z star. Z star plays a role in alpha. This is a specific point at the holographic direction. And Z, this is a holographic direction. And this formula, these two coupled integral, is necessary to compute the entanglement entropy. So when you want to compute the entanglement entropy in a holographic way, you need to do these two integration. Okay? So this belongs to this problem. Okay? Then we know entanglement entropy at the boundary, then we can ask what is the bulk field, for example, in Blackman factor, giving this boundary data. Okay, so it's a summary of the idea. So normally, yeah, there are many complicated or deep idea of the physics or mathematics in the field, but you have experience at the end. It boils down to some differential equation or integral equation. The holography is the same. Actually, we have to understand many things to really understand the holography, but the computational sense, it just boils down to the equations, differential equations, integral equations. And the whole point is, in a traditional way, A, B, C, D, the red one is already known, and you just straightforwardly solve. But now, our question is inverse. It's inverse problem. A, B, C, this red one is not known, but we only know the boundary value. Then, in order to match the all boundary value, what the bulk field should be used? So that's the question. And we can use the machine learning to get the bulk fields. Okay? So this is classified as an inverse problem. And in some sense, it's optimization problem because our loss function should go to 0. Okay? Good. So that's the, I think I finished the basic scheme. Now let's go to the problem I really want to solve. Maybe this part I need your feedback. So here, in terms of ADS-CMT, this QPrep or non-Fermi liquid is the most popular subject. And I think it's because there's a universal property of this non-Fermi liquid. Here, universal means the microscopic structure or constituents may be very different depending on the methods, but somehow some property is universal. So, for example, the DC resistivity, the linear T resistivity property means as temperature, in terms of temperature, this resistivity is linear for many different materials, or in particular for the strongly correlated electron systems. And there's another one, it's called the Hall angle. It's also measured at the finite magnetic field. In the finite magnetic field, you have two kinds of conductivity. And the ratio of these two kind of transversal part and longitudinal part, the ratio is proportional to t squared. So it's arguable. This is really the universal property of the strange matter. Of course, it's arguable, but I think as a zero-sort approximation, as a theorist, this is a very attractive property to understand. So there was a review paper in Science. The title is very interesting, Stranger Than Matters. And here there's a table explaining the current status of the universal properties. And here there is a linear theory. There are two things, high temperature and low temperature case. This is a whole angle property. Of course, in some materials, the whole angle was not observed. So maybe already here people can claim, okay, you don't need to worry about this. This is not universal. You can claim that. But again, as a theorist, it's as a zero sort, I think it's enough universal enough, right? So then this is experimental the summary. If we go to the theory, then there is a traditional ADS at the CMT theory explaining t goes to 0. And also interestingly here, it's SYK model, ADS CF, AD EMB model says also explained in some way this linear theory distribution. However, interestingly, there's a missing part here. Here there is a whole angle t squared, but here there's no whole angle t squared. I don't know why, but maybe there's not many things to highlight in terms of theory. So I may be wrong, but in the holographic model, there is no, consensus about the t linear distributive plus t squared whole angle together model. But there are some models explaining this one, or there are some models explaining this one, but there is no consensus on the explaining both at the same time.
Yeah, in the proper brand limit. Yeah, we can do.
Yeah.
But in the fallback direction,
Yeah.
I don't know.
Yes, yes. So it's very simple problem to ask, but very hard to answer, right?
Yes.
This is the machine can do. This is the problem machine can do. Maybe the human beings are lack of imagination. Yeah, sometimes if we know the answer, then we can understand. So that's my basic motivation to understand this ADS-CMT by using machine learning. So this is our favorite model. Actually, many people, Lee also a worldwide expert on this model. So this is called Einstein-Maxwell-Dulaton model, very simple model. So we have Einstein terms, scalar terms, and Maxwell terms. And here, this is called axion, but it is introduced to for the momentum relaxation. So here there are three unknowns, Z, V, Y. Okay. So when this model was introduced for the ADS-CMT, what people did for the first time is very, very traditional way of science. Okay. Normally, theorist does not like numerical work and wants to do some symmetry or some the universal property using the IR dynamics, something like that. So people just assumed Z is this exponential form, V is this exponential form, Y is this exponential form. And this is very clever because by assuming this, the metric is solved in this way. Here we have three parameters, gamma, delta, lambda. Here we have three, theta, z, zeta. They are related, the three parameters, but we have a very nice metric form here. By using this very nice form, we can understand why the distribution can be linear or not by using this. Okay, this is very clever. However, to my understanding, there are some models predicting linear t by using this, but no t squared yet. Maybe I think the conclusion is there's no case, right? Maybe that's the conclusion in this setup.
Yes, I
Right.
agree with you.
Right.
with Elias and Sarah, we can do the proper limit. In that setup, you can find some regime
Yeah.
have both linear and particular behavior. But as you said, with full back direction, no model.
Right.
Yeah, no model. Yeah.
Then probably the next step is we have to add more terms. Then maybe this will be more complicated. Sometimes it's not analytic. But anyway, that's one of the theoretical possibility you can modify by adding something here. Okay. So I just made some sequence here. For example, this, let's say this blue one is the capacity of this model, original model. But this green circle means we just assume ZBY has this form. That's the green circle. But we have still room here. We don't need to assume this. It has more potential to explain something. And with this, you can add more terms. You have some variance. That's this red one. You just modify this model by adding more terms. And another possibility is just forget about this. There may be better model. That's, I think, it's in the purple case. So we have many, many possibilities. What I want to do is very humble. Let's not try some dramatic things, but let's try to understand this model better. Maybe this part. People already, I mean, the many analytic work, it's already exhausted. I mean, green part is fully understood. And this part, I think it's not analytically approachable, but still numerically we can explore. But this is too wide area to explore numerically. You have an infinitely many way of choosing Z, V, Y, right? So my point is we can use machine. We are busy, but we can use machine. The machine can explore this area. And that's the point. Right? Good. So then that was my middle ultimate goal. And in order to do that, let me just introduce what I did as an exercise. The exercise is two exercises. One is a deep learning bulk space size from boundary optical conductivity. Here, the big data is the optical conductivity. This omega is the frequency. So because omega is a continuous variable, we already have a big data. So for a given optical conductivity, we can ask what the space-time metric should be. So this, for example, this red one corresponds to this red, and here this blue one corresponds. This is in Blackman vector by using the different chemical potentials. This is just exercise. We didn't use something new. We didn't learn something new because everything is already known. This is a very simple model. Everything's very easy. But you know, this is again standard. I mean, strategy to learn something new. So this new numerical strategy, machine learning strategy, should be able to reproduce already known result. So this is kind of exercise. Another exercise I did is the entanglement entropy. Entanglement entropy means basically, so here there's a one-dimensional line, and we can define entanglement entropy for different L, because L is a continuous variable, so you have a big data. And entanglement entropy at the boundary has something to do with the extremal surface area here. And as I said before, it has something to do with the integral. So here, this is the entanglement entropy data at the boundary in terms of L. And we can ask what is the metric here. There's a metric. We have two components, the G and H. And G and H, so you can see the machine learning found correct G and H. It's already known by using this big data. Okay. So this is two exercises.
But in the first plot, the blue one, we see the clear deviation on the right side.
Yes.
Yeah. One.
Right. Yeah, we tried to minimize this, but we failed. But it was okay for us because it's exercise.
Yeah, your H is good, but the G is
yes,
not good. Yeah.
Yes.
I
agree.
Yeah. I see.
Right. Now this is the real one. After doing two exercises, okay. So in order to actually, our ultimate goal is to find to check if the EMD model can find some potentials for linear t and the whole angle t squared. But it's a too difficult problem. So let's first focus on the linear t problem. And of course, experts will say, okay, this is already solved. We know analytically what happens. That's true. But again, we can ask this question. Suppose we don't know the analytic solution. Then machine really can find it without any knowledge about analytic form? I think that's again the effective question. If machine learning is really good methodology, then it should be able to reproduce some results, analytic result, without help of the analytic result, right? So that's one thing I want to say. So it's the same thing. Okay. So in order to do that, let me explain another method. I'll be back here again because this is technical. Okay, I'll be back here again. Let me show the result first. So this is an EMD model, and this model is called the Gupsa-Roca model. The reason I'm showing this Gupsa-Roca model is Gupsa-Roca model is the one very standard model explaining linear T resistivity in the EMD model setup. And the question is, okay, let's suppose we don't know this, and the machine can really find this model by himself, by itself. That's my question. So in order to check that, this is the test big data. So actually we didn't use this one. We just used this part, right? So red is linear, orange is linear. Do not look at this. Everything is linear. Then the question is, machine can find out the corresponding potential V and Z. That's the question. Actually, there are three things: Z, V, Y. But we set Y equals 1 for simplicity, because our purpose now here is to check machine really can find out Gupsa-Roca or not. In the Gupsa-Roca case, Y is 1. So in order to test, we just set Y equals 1. And we didn't say anything about this. And we just gave this linear resistivity. And the machine's answer is this. Depending on this color, the color difference is everything's linear, but the slope is different, right? Only one slope matches this Gupsa-Roca. The other slope is different from the Gupsa-Roca's case. Then by using this, this is the machine's result. The potential V is almost same. Of course, a little bit difference, but there's no big difference. But there is a difference here, Z. And you can see here, this yellow one is Gupsa-Roca case. It's a very smooth, linear, and goes to the saturated values. And that corresponds to this value. That corresponds to this value. So machine precisely found this potential with some error. So then I cannot say precisely, this is numerical one, but the reasonably precisely exponential value, and this reasonably the value, right? So then the first conclusion is machine is able to find out Gupsa-Roca. That's the first lesson we learned. And I still pretend we don't know anything about this analytic result. But one thing I can learn from this machine learning is this linear behavior has something to do with largified behavior here. And this the common thing of this largified behavior is it's always 1 over square root 3/5 here. But the multiplication factor is different. If this is 1, that's Gupsa-Roca. But if it is not 1, then it's something different. But the whole point is, if you have some potential at the largify this exponential behavior, that will give you the linear resistivity at low temperature. That's what machine is telling us. Okay. And here you have this bump, steep behavior. That is reflected here. You can also see the bump, and this dip. So this part has something to do with this. And this flat part means Z phi goes to 1. This is the ADS condition at the boundary, a simple ADS condition. So somehow we can qualitatively understand, okay, in this framework, what's important? What's important is Z, not V. And the Z behavior here has something to do with here. And this linear one is related to the exponential behavior, something like that. So we learn from the machine.
One more question. So in your scenario, when you consider the machine learning, so do you consider any constraint on the capital Z, so that in the UV, Z goes to 1? Do you consider this constraint?
Very good. Yes, we impose already.
I see.
Very good. That's a very good point. Here, in principle, mathematically, we can just set everything free. However, we have a physical constraint, and the solution should be asymptotically AES. Then we have to impose that. So this part is not machine found. This is our constraint. The constraint we imposed already.
I see.
Yeah.
I see. Good. Thank you.
So just an exercise. So we try to use this one. This one is a little bit different. It's a linear, but we have a finite intersection, a finite residual resistivity. So by using this data, we wanted to check what's happening for the Z potential part. So as you can expect, here the characteristic thing is the exponential behavior. But here, if you have this residual part, the exponential behavior just disappears. And it's saturated, the potential saturates some value, and that value has something to do with this value. Okay, something like that. So again, there's some concept here, and then there's something to do with this. Okay, so this is very preliminary. So I don't claim I learned something very interesting here. No new physics here, but we have a clue what we can do. So my point is here. First conclusion is machine can really find out the groups of local numerically. That's number one. And then number two, just by looking at this potential term or by changing this potential term, we can see the change in the resistivity data. So then if we really want to have a linearity and t squared the whole angle, then we can see what's changing here. Okay, so then we can learn something. Then, for example, suppose the correct answer is this one. Suppose, of course, this is another answer. Then we can immediately ask, okay, something happens here, and this has a physics. Then we have to understand what's the physics behind this. But without this numerical result, everything is perfectly okay. So we don't see which part we see. But now, if this is the case, then we say, okay, we have to look at this part. That's what I want to get from the machine learning. Okay. Good. So maybe I
have enough time. Don't worry about time.
Okay. So then this is everything I want to tell you about the big, story. Why I want to use the machine learning, and in what sense I'm using machine learning. So then the last one, I can explain a little bit about the machine learning itself, if you are interested in.
Yeah.
May I continue?
Yeah, yes.
Yeah, you can stop me anytime. Okay, so now let's talk about the machine learning technique. So, okay, so this is the very basic building block about the deep neural network. So this is not deep neural network, this is one neuron. So the idea is very simple. In the neuron case, you have some inputs. In case you have 3 inputs, and you will have some outputs. Okay, so from input you have to decide what output is. Then here the idea is very simple. Sometimes the x1 can be weighted by w1. So sometimes you have to determine this is important, this is not important, something like that. That it will be you can assign some numbers and you can weight the importance of these 3 guys. Then this is w1 x1, w2 x2, w3 x3. This whole number you got now. Now you have to decide this number is really big or small. Then you need a reference, right? This is your reference. For convenience, you can think about this is a minus E, just for convenience. Then you said, maybe I have an example here. Okay. So 0.1, 0.1, somehow this is your input. And W, 1, 2, 3, just I made 1, 2, 3. Then after computing this, you have a 0.7. Then you have to decide if this 0.7 is really big or not. You need a reference, right? Then if in this case, for example, you have a 0.7, and if you add, for example, how can I start? Yeah, sorry. Let me do again. 0.1 times 1, 0.2, then this is 0.6. Then if your B is 0.1, then final answer is 0.7. And if your the B, wait, this is called the bias. How biased you are. Then if it's 0.5, then it becomes 1.1. Then you have to determine this is big or small. And then this sigma is called the activation function. For example, if I use this activation function, then if this argument is 0.7, it's 0. If it's 1.1, it's 1. So you turn on or turn off. Okay. So when you decide that, this bias also important. Okay, that's what happens. It's 3 numbers, weight, give bias, and decide on and off. Okay, that's how you your information is transferred. Of course, this activation function, this is very conceptually easy to understand, but you can use different, more smooth activation functions. But this is very technical part. I think this is called a rectified linear unit. I mean, this is a very popular one people are using for deep neural network for the technical reason. But anyway, this is basic idea. Now you can connect. This is just one thing. Then you can connect in this way. Then, for example, this is your one input. Then you have the 2 weight, right? And then here you weight and bias will determine. You will give some numbers here. Then number will weighted and biased. Then and the output number will be weighted and biased. And finally, you will have some number here. So you give some number, and after doing this network, you have another number. This is a function. So here Z, you can imagine the function Z0 from 0 to 1. Every number of Z, of course, discrete number, will give some number. That's a function, right? So that's how deep neural network is used. You can just construct arbitrary function by using this deep neural network. What function is decided by these W and B's. Okay. Good. So then let's have some exercise here. So this is the data, this curved data. Now we want to make a function, fz, feeding function for this data. Okay. Then so if I make this, so this is basically, you can simply imagine I have 2 numbers and this corresponds to this, and that's a bias factor. And this tangent hyperbolic is my activation function. And you have this number, and the number will be weighted by this 2 by 2 matrix here, and add bias, and again activation function, and weighted by 2, like that. So then this box is all parameters you can change, right? Good. Then, so this is the final result. So actually, I prepared the animation, but this became PDF file, so I cannot show that. So what's happening is you start with this red line, and machine is changing this line, and at the end, it just fit this. In order to have this curve, these boxes must be this number. Right? With this number, you just give one Z, then it gives you correct FC. So this is strange looking numbers. Sometimes people say, okay, because of this, there's no physical meaning for this neural network, because just a random number looks like a random. I agree with that. In this case, it's just a random number. Right. And then, so okay, in this case, it's a 19 parameters. The number of boxes are 19 parameters. You have to change the 19 numbers to fit this curve. So in order to visualize, you can think about this curve this is the surface in 3 dimensions, but actually this is the surface in the 20 dimensions, right? This is the 19 dimensional space, and you have 1 dimension here. So then the point is, every point in this 20 dimensional space, you choose one, that means you choose different number, then your loss function will not be 0. And you start from here, for example, and the machine try to find out here, because the loss function should be 0. Then this is now a mathematical question. You have a surface, very complicated surface in 20 dimensions, and you start with some arbitrary point. How you find out the global minimum, which is 0? Now this is a very complicated problem. Don't worry about that. That's not our job. We can borrow some package from the machine learning guys. Okay, so we just borrow. Then the basic idea is just to follow the steepest descent way. That's just one way, but that's not that simple. So the machine learning guys developed many methods how to find out the global minimum. And as Lee asked correctly, we don't know if there is a really one global minimum or many global minimums, or sometimes you just go to the local minimum, it does not go out. Yeah, you can easily think, so you just follow this way, you just go to track the local minimum, you never go out. But you don't know you are in the local or not, right? So then machine learning guys already know that they are not stupid, and they developed many methods how to escape from the local minimum. Okay, so that's the thing. And there's another general question we can ask is this a unique design? So Lee asked about how layers. So this is number of layers, 3 layers and 2 nodes. However, I can also do this.
Yes.
And then, of course, by using that, I have 71 parameters, much more complicated. And this strange looking number is the correct numbers for this design. So there is a very interesting mathematical theorem. That is the universal approximation theorem. That means you can always find the deep neural network design to fit any arbitrary curve. So you just give any arbitrary curve fz, it can be very complicated. But you can always find the machine learning deep neural network reproducing that guy. That's the universal approximation theorem. But you feel something strange because you can imagine many complicated curves. It's very complicated curve. Then if I use, then probably you think maybe I cannot reproduce that complicated code just using the simple one. Sure, that's true. This is the existence theorem. Then the answer is you have to use more complicated one. Then if you are using correct one, then you can always find out any curve. Okay. So then that means again you need some experience. Sometimes this design is wrong, then you cannot find the correct answer. But you can say this way, okay, then maybe we can use a very complicated design from the beginning. Of course, then that will be okay. But if in that case, you will spend a lot of computing time because these parameter numbers will increase much more. So you have to find the optimized design.
I see. So my question is regarding your theory, so it's an NP problem or is solvable with a P problem?
That I don't know. So I don't understand the terminology NP and P.
In some sense, so maybe the system is very complicated. Maybe you have infinite number of parameters. So in practice, it's not durable. Yeah. In principle, you can, but in practice, you cannot.
Right. I don't know the answer right now, but in this case, what I want to say is just finding out the correct design itself we don't have a general, nice principle. It's just a trial and error.
Yeah, because we know in classical mechanism, we know when we're waiting for long time, every particle will recover to the inertial point.
Yes.
Yeah, but the time is
Yes.
unacceptable. Yeah.
Right.
But you see the story, if you have very complex system, maybe we cannot handle. Yeah.
Maybe.
Although we have a principle to say.
That's right. I agree. Yes.
I see.
Okay, so that's the basic idea of the any more questions about this deep neural network technique? So if you are not if you don't have any experience on this, it looks very scary, but you don't need to worry about that. I mean, even undergraduate students can do this after 1 week. If you understand the Python. That's a preliminary knowledge. Okay.
So Mathematica have also a tool for this.
Sure. So actually, I used the Mathematica for this one, but I wouldn't recommend. If you just do the research problem, this is too slow.
I see.
Time is important. But this simple problem, of course, Mathematica can do that.
Okay.
Okay. So I'm going to go very fast. So this is the holographic computations for the. Okay, let's just skip that. It's not very important. Yeah, so let me just skip. Good. So maybe let me summarize with the outlook of the. Yeah. Okay, so now what we are doing is we are doing some two things. We first need to understand and develop the methodology. So how to use the machine learning for ODE, so this is very interesting idea, PINN. Maybe I can explain that later if you want. Maybe I like this name, physics informed. So we need the physics. It's not just a black box. And how to, I just focused on ODE, but PD part is also important. And we can use another physical quantities to understand to use the machine learning, like Alpers data, fermionic spectral function, and more quantum information theoretic properties like complexity. But anyway, so my ultimate goal is to try to understand this linear T and T squared model. And regarding that, I'm now here. So in summary, I would like to explore this blue regime by using the machine learning. It's not guaranteed, but maybe, I don't know, but there may be some model here, but there may not. Then I have to extend the red, and maybe there may be not. Then I have to extend the purple case. But here, in my opinion, very important restriction of my method is I have to start with some fixed action.
Yes.
And in this fixed action, I'm trying to change ZV1. However, if the really machine learning should be powerful, then machine learning should give you the action itself.
Yes, that's one question I want to ask. So maybe because we have in the form of the action, maybe you have find no answer.
Yes,
possible.
Yeah.
For example, here you consider linear resistivity.
Right.
We know some recent experiment from conduction matter. We say the resistivity at a strong magnetic field will scale like T square plus B square square root. That's a new development.
I see. Okay.
Yeah, I think in this set of action, I think maybe cannot.
Right.
Yeah.
Right.
Using machine learning. Yeah.
Yes.
Maybe you have square root or something else.
Yes. Right. So there are many limitations in this approach. But I think it's
still power enough.
Yeah. So worthwhile to try. Okay. Thank you very much.
So last slide, we say you like physics informed network. So I see another name, the physical driven neural network.
Oh, I see.
Yeah, physical driven. Yeah,
Okay.
something like this.
I see.
I really like physics.
I see. Yeah. Yes. Yeah. So in this area, there are many developments every